Hi, let's talk today a little bit about momentum, something very useful, potentially in your self-defense. So it's basically Newton's second law that's just revisited. So we start off with force equals mass times acceleration. Well, what's mass? The change in velocity over time. And if you look at change in velocity, that's final velocity minus the initial velocity. So you end up with that. You expand the terms and you get this, and you get two little expressions there, mv. That's what we call the momentum. And we'll assign that the letter p, lowercase. And it's mass times the velocity of the object. It's simply a measure of this. Now that mass is a scalar, velocity is a vector. Multiplying the two, you actually still get a vector. So momentum is a vector, it has a direction. Okay, and that's quite important. The units, nothing fancy here. You can interpret it as kilograms meters per second, but it can also be Newton seconds. Take a little look at that and you'll see why that makes sense. There you go. So the change in momentum here represents the force times the change in time. That's a little bit tricky because it assumes that the force is constant here. Now, if we knew some calculus, we could get a little deeper into this, but for now, we'll just look at it like this. Now, this change in momentum has a specific name, impulse. Okay, that's what it means. So it's the change in momentum. That's usually what we refer to when we talk about the units Newton seconds. Okay. Now, if you look at a graph, I think you'll see that this makes sense. If you look at the force time graph, the area under that would be force times time, which we now know is the change of momentum or the impulse. So it'd be quite straightforward, and you could just use the equation if the force was constant like this. But there may be situations where the force is not constant. Be very careful about that, because then it looks like a little more like this, and then you either have to use calculus or some sort of geometry, or simply estimate what the area under that curve is. Okay, so you could be asked questions about that. Conservation of momentum. That's when bodies in a closed system interact. The total momentum remains constant, provided no external force acts on the system. Okay, what does that mean? It means that the total momentum remains the same before, after, whatever something happens. So for example, if you have two objects and they collide and they bounce back like that, if I calculate the momentum before of both objects, and it should be equal to the momentum of both objects afterwards. So a little calculation, you always start off the same way. The momentum before equals the momentum after. Calculate these values. If you have any unknowns, leave them there. Okay? And what's very important to notice here is that the momentum is a vector. So direction is important, therefore positives and negatives matter. So keep those in mind. For example, here I assign that left was positive. Okay? Conservation momentum also applies in two dimension. All you do there is you break up the problem in a horizontal and vertical way. So you end up with this problem. Now here, if you look at it, you could break it up horizontally and vertically. Horizontally speaking, there was an initial momentum, but in this case, vertically there was not. There was zero vertical momentum. So you end up with two separate situations that you can analyze. This is good if you have two unknowns. So you'll end up using two equations with two unknowns. And you can pause it, take a look at that little calculation. Hopefully there's no mistakes, and it should work out. Now, is your system closed? It's important to remember that the momentum is conserved if you consider all objects that are involved. When you do this, the system is said to be closed. So right here, on a baseball throw, for example, if you're just throwing something, you've just given that baseball a whole bunch of momentum, right? It went from zero momentum, because it has zero velocity, to some large quantity of momentum. Well, you can't just create momentum out of nothing, right? Momentum before equals momentum after. So if you gave the baseball momentum going towards the home plate, then there had to be some sort of momentum going backwards also at that same time. Where does that come from? Or where is that? It's the actual pitcher who moves back. Now, you won't notice it because he's much more massive. Also, his feet are connected to the ground. Therefore, he can transfer that momentum to the actual earth itself. So, and the earth is rather large. So, if you're trying to change its momentum, it'll be very, very small kind of change in its velocity. It's so massive. Remember mv. And so by throwing a baseball forward, technically you're actually moving the earth back a little bit. But it's so small that you'll never notice it. Okay? So it's a tough concept, but think about it. If you jump up in the air, you've just given yourself a lot of momentum upwards. So what went downwards? Well, actually the earth moved downwards a bit. And it's the same when you're coming back down. All of a sudden your momentum goes from going up to down. It's changed. And if it's going down, something's got to be coming up because your total momentum at the beginning when you were just standing there was 0. The earth actually moves up a little bit to meet you. The earth is so massive though, you don't notice these things. In space, it's a little more obvious. Here's a fun little one. Somebody decides to play baseball by themselves, and it is possible to do it. There you go. Change of momentum. So when he does something like that, when he hit that ball, he moved back a little bit, and it may be easier to show these things. It may be easier to show these things in space, but not as easy on Earth. So if you look at a few problems, if you've got a wagon that's moving, a train moving forward, and it's going to collide with 3 others, and then they all move off in the same direction, right? What's their final velocity? This kind of problems. Well, at the beginning, the momentum was coming only from that red cart. And afterwards, the momentum was transferred to 4 of them. So momentum before equals momentum after. You can figure these things out. In this case, it didn't matter what the mass was since they were all equal. It cancels out. And you simply get a ratio of their velocities as being important. And the final velocity is 2 meters per second. Okay. Another one, a cannon, right? If you fire a cannon, before you fire it, the momentum is 0. After you fire, you got a kind of a high-speed cannonball going forward. There will be what's called recoil. The cannon will move backwards. Okay, that's conservation of momentum. It's a really nice example. Calculating it is not that difficult. Okay, the momentum before was 0. The momentum after, well, you take a look at it. You have it allows you to calculate what the velocity is of the cannon. So it's going backwards at 6.7 meters per second in this case. Very nice. The second part of the question was it's stopped by 4 ropes. Say it's tied so it doesn't go rolling around. So how much force would be on those ropes? Well, we know that the net force is equal to mass times acceleration, right? You got 4 ropes, so it's 4 times the force of tension on each rope. Would have to be equal to 200 times the acceleration. And you need the acceleration here to figure out the force of tension. So we have to go back to some of our kinematic equations, figure this out, because we know how far it's moved, and we could work out what the acceleration was, and then put it into the equation, get our answer. Okay? Another question, tennis player swings a racket, hits a ball. That's a change in momentum again. We can look at it that way. The ball was moving towards her at a speed of 21 meters per second, rebounds at 39 meters per second. How fast is a racket moving immediately after the impact? We can figure that out. Momentum before equals momentum after. Put in the right numbers. You end up with the answer, 7.4 meters per second. The second part of the question, if you know how long there's been contact between the ball and the racket, you can actually figure out what the average force that the racket exerted on the ball. Okay, I say average because with these equations, like I said before, you assume it's the force is constant, and it's not actually true. So we have to say just average force. So you work these things out. In this case, we'll use the impulse equation and work it out, and you end up with 327 newtons. And that's it. A last little picture from the great